welcome to ECGR 4101, 5101. This is lecture number 3. Have any of you gone out to look at lecture number 2? I'm so excited. I just have to show this because I'm so proud of myself. I'm just hoping I don't break my arm patting myself on the back. I guess nobody's ever heard that phrase before, huh? See, you're not supposed to do that. So, of course, to go to our class, you can just do a Google search for me, classes that I teach, embedded systems, notes. And now I have actually discovered how to actually put the files on one whole thing. And let's see how this goes. So, I thought you would appreciate that, huh? So, does that mean you don't have to show up for class? No. Again, I give quizzes every so often, so this is just a supplemental in case you need to go back and take a look at the notes. The other thing is that I may very well have to offer this class next semester electronically, so the recorded lectures will be available for them. So I'm in. Oh, I got to show the end too, right? I like that. Oh no, thanks. All right, here I should make a vote. This is where I take the votes that if you're late for a quiz, you know, you missed the quiz. So make sure you get here on time. You got to make sure you turn it in when I get the quiz. Thank you very much. You can turn that off. Yeah, I thought you would get a kick out of that too. All right, so again, available for you to take a view online. I did also remember I'm putting everything on the main pages and the announcement pages when things go on. I'm not going to have to remind, or I'm not going to remind you again and again. Lab assignment 1 is due Monday the 12th, so it's a little bit longer than what I originally posted. The next homework assignment is due September 7th, and I'm going to be able to finish all the materials for getting you ready for that, for the homework assignment. And textbook chapters you can print out if you would like. Remember, this is an open book, open note test, so you're welcome to print out the book and bring it with you to class, to tests, to whatever. Again, one thing I asked is make sure you don't store it and post it somewhere else, because we're still changing the book and I don't want anybody else to come back to me and say, well, on this page you say this. Well, that's the pre-release version, so I fixed that. So make sure you don't do that. Homework assignments, as always, here. Assignments 1 through 12, Chapter 2, you should be able to finish it after this class, no problem. And then, of course, lab, including the assignment and the supplemental information. I have one person regularly point out to me the errors I have, in other words, bad links and stuff. So who sends that to me? Okay, so thank you very much. You get a free trip to the prize closet for reminding me on things wrong with the page. You think I was going to yell at you?
No.
No, good. So I do appreciate comments saying this link is broken or something's not clear here. If there's a misspelling, yeah, you can tell me that too. All right, let's go on. We are going to start up with our content. The last thing that we had talked about was the specific assignments of pins, or I should say being able to identify what pin is going to be input, what's output, direction. Remember the direction of a pin? And we also had an example of which way is going to be identified as input, output, direction, and to go ahead and read it. So, I think I wanted to point something out. No, I did not. So, you know, some of the stuff we showed earlier was just kind of like a pain. So, we had port D, DR, bit, B0, and that's interesting, but you know what? If I were to look at the board, I would rather see something that said like LED 0, LED 1, LED 2, etc., or switch 1, SW1, SW2. And so on C constructs, what do you have that will do that for you? To rename something to something else. What is it called?
Define.
Okay, it's a pound define. So it's a macro that will, in the middle of your code, you could write something like, as I said, this would be better to be LED 1 as an example. So what we could do is we could actually write the code pound define, and we'll call it LED 1, and then we'll say port D.dr or .dr.bit .b0, which means that now that specific bit on port D will be called LED 1 later on, so that we could write some code that looks something like, well, by the way, we could also do another pound define, and we could say LED on, oops, and we could say LED on is going to be 1. Because you never know when we might change our board to make it a pull up resistor. No, pull down resistor for the LED. I got to figure out how that works out better. Well, we might want to change our circuit later. So we'll say LED 1 is to turn it on, and oh, by the way, LED off of 0 to turn it off. So that way, later on, whenever we write some code, we can simply say LED 1, by the way, I should write this better so you can tell it's 1, is equal to LED on. So that is just a simple line of code that will turn on the LED. And you don't have to remember what port. If you happen to forget how, is one LED on, LED on, you can't remember what it is, then you use these macros to just define it easily. In the same way, you can use a pound define for your switches. So in this case, we'll say switch 1 is going to be equal to, in our case, port 4 dot bit 0 as an example. And later on, we could just say something like, if switch 1 is equal to 0, then turn LED 1 on. All right? So is this correct C code, by the way?
No.
No. What's wrong?
Totally.
Ah, is that what you're going to say? You think I did this on purpose, right? Yeah, I did this on purpose, right? The most common bug in C code is to use the assignment equal when you really mean to test the equality. And so, if you happen to notice, I did leave space there for the other one. Uh-huh. There's a method to my madness. There really is. Look at it. It's perfect, right? You don't believe me, do you? By the way, what's another way I could have written that line?
If not on software one.
All right, if not, switch one. So, in other words, if so that's another way of doing it. You think there's another way of doing this as well? Yeah, I did, probably. So, I did say something a little bit erroneous last class, and so I want to fix that up. And that is, let me find out exactly what I said last class, and I'll have to fix this. So you'll need to look in your notes. When you are working with an input port, if you want to read the port instead of the data register associated with it, in this case, you need to actually say port. And that's one thing I erroneously did in the last class, so if you can make sure to fix that in the example. And I believe there's probably one other place I did that too. And it's page 4. Should have done this port as well. Can you put those back up? So, using macros is lots of fun. I think everybody should do it lots and lots of times. So, rather than having you write by hand things that are basically in the book chapter, specifically, if we have this small file here, I just want to point out some important aspects. First of all, you notice here, it's all pound defined. We're identifying the LEDs and also, what is this for defining? DDR, data direction register. So in other words, that's to say, I set it later equal to 0 or 1. One will set it as an output. 0 will set it as an input. So we specifically have to go out and set it to a 1. But we'll see that later. So here's all those pound defined. So now you know it's really easy. LED 9, data direction register, it's going to be port E, bit 0. That's really some detail that you need to worry about once and then you can forget about it. So getting back onto the next part of this, this is where I helped you identify that, LED on, 0 and 1. By the way, can everybody see this fine, or do I need to zoom in? And in C code, notice that what we can do. If, again, with macros, you have a pound define and you have something, and then notice it's inside the curly bracket here, goes all the way to this curly bracket there. All it does is the macro, when you go through compiling, it replaces any instance of all underscore LEDs underscore on. It just replaces that with the code LED 1 equals LED 2 equals blah, 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 equals LED on. All right? And then the macro also says, oh, gee, LED 1 means port this, port that, port that, port that, port that. So this is, you can imagine if you're turning LEDs on and off, you really don't want to lose track of, okay, LED 3, was that port D bit 4, 5? I can't remember. So, easy. You define it once, and then you use it again and again and again, just as LED 2, LED 3, whatever. And then you can make these neat macros, because later on, if you want to say something like enable LEDs. Well, let's look at what enable LEDs say. Well, it says right here, enable LEDs, and it gives you all of the LED directions. In other words, it's telling you that, all right, I'm now going to set up all of the pins on the microcontroller that are set up for these 12 LEDs. I'm going to turn them all on, or make them all outputs. That's the joy of macros. And in the same way, you can also identify things like, remember we said all LEDs off? Because earlier we just said turn them all on. So in your code, it makes it really easy to read. If you are pressing switch 1, and in fact in this case with the 0, I would have actually wrote here switch off and defined it up here. So in fact, turn to your neighbor and tell me, or between the two of you, the pound define, write the pound defines for switch off and switch on. So write the pound defines. Let's see if you understand what it is. So like you have the pound defines up here for the identifying switches and LEDs, what will be the two pound defines for identifying is the switch off or is it switch on? In fact, call it switches off, switches on.
Right out of space. No, there are no
All right. Is anybody not done yet? Good. I'm going to call one person. You said you're not done? Okay, good. I'm going to call one person who didn't raise their hand. Come up and show me their pound defines for a trip to the prize closet. Ah, look at this. Have you been to...
There shouldn't be any setting. Although one of my definers was.
Ew. We'll see. SWF.
Yeah, off. I need
Okay. Well, I'll tell you what. I'll do mine. I'll show mine because that's correct. But I'll show that. Actually, that's not correct. Or that's not right. Let me show you. Here's what I think. You still get a trip to the prize closet because you're brave. I did this. Pound define switches off is equal to 1.
Why?
And switches on is equal to 0. If we looked at the circuit right here, remember it says if switch 1 is equal to off, or is equal to 0, that means you've actually pressed the switch. Remember what was going on? We had the pin. And we had the switch, which was tied to ground, and we had the pull-up resistor, which was tied to VCC. So, if VCC is what's going into the microcontroller, then it's going to measure logical 1. If you press it, then the drop in voltage from here to here will go from VCC to 0 because it will tie directly to ground. See, that confused you, or that you forgot about that, right? That's one of the advantages of doing a macro. Because now look, I'll embed switches off inside my code, and I will never mess that up again. Of course, I'll forget which is off and which is on, and I might have to remind myself much later. But now I know for sure that when I use switches off, we're checking to see if it's off. So our code later will be something like, if switch 1 is equal to switch is off, then let's see, what were we? LED 1 is equal to LED on. So now we've taken you away from having to remember what zeros and ones are, how it's wired on the outside. And is that helpful for running the code correctly? Sure. I mean, you'll not mess it up. That's where your bugs will be later on, because you forget that switch 1 is, or that 1 is off and 0 is on, which is kind of different than what you would figure in your head. All right, easy enough. Everybody understand that? This is general embedded systems that you need to think about. Oh, by the way, that pound define, I put no semicolon after that. Why is that?
It's not a statement that gets executed.
All right, it's not an executable statement. It's actually a replacement. This symbol right here, switch is off, will be replaced with the number 1. And you don't need a comma or a semicolon. Now, where you did see that before was here. Like in this line right here. Pound define LEDs off. I keep on going and going and going and going and going. And there's a semicolon there, right? But what else is there? The closed bracket, the open bracket, which means that whenever all LEDs on appears, that means you're going to replace it with, starting with this L, ending with that semicolon. So where do I use it? So that may actually be incorrect on here. Yeah, that doesn't matter. An extra one doesn't hurt you. So when it sees all LEDs on in here, it's going to replace it with LED 1 equal all the way through LED on, and then it's going to put 2 semicolons, one right after the other. Is there a problem with putting 2 semicolons, one right after the other? No, that's fine, because the compiler will see that as an empty no line. You might get it depends on the compiler. You might get a warning, but it will still compile. So it might be slightly ugly, but. All right, I think I beat that one to death. Let's go on. There is some additional information in the book talking about loads. And so if we have... ooh, wow. You can see every pore on my arm. So, if we have an output from a microcontroller and you source current, and for that matter, anything that draws current or sinks current. What were we talking earlier about the microcontroller? How much voltage do you have? Yeah, 0.9, 1.8, 3.0, or 3.3. Even if we're running at 3.3, do you think it's going to be able to provide a lot of current to run a motor? You don't want to drive motors with small little itty-bitty digital lines coming out of a microcontroller because, frankly, you don't want that much current flowing through the chip. So what do you usually use? Okay, we heard H-bridge, and you set up there?
Motor driver.
A motor driver, which is like an H-bridge or something like that, or a plain old transistor. So if you have anything that you're outputting, you usually will introduce something like an H-bridge motor driver. And rather than draw this whole entire thing the same that's in the book, I'll just start it up and you can get an idea of this. And they call it an H-bridge because it looks like the letter H when you complete it all. You know what, I'm going to have to do it just to show. And this will also be one of the lines that comes out. And this will be your motor in here. And then you have another transistor. Oh, heck, I might as well just finish it. So that's an H-bridge. So look what you're doing. You have two output lines, and this could be, for example, port D. This could be bit 0. This could be bit 1, as an example. And you could use it to control your motor. And you would use, what type of instruction would that be? Something like you used with... What device did we see that we use this with? An output device. How about an LED? Yeah, thank you. And another trick that we use, I won't do this. A keyboard, actually, I won't do the keypad matrix one. I think that's pretty obvious as well. All right. Let's get into analog signals. 20 minutes. Analog. There are a couple of basics that I want to cover with analog. That being, remember analog is what kind of voltage? Continuous. Digital is discrete. So if you have a certain number of bits to represent all of the analog signals that are available, obviously you're not going to be precise the entire time. In fact, what you're going to see is something similar to this, where let's say we have a total of 4 volts, and we have to represent the value between 0 and 4 volts with only 4 bits, right? There's going to be a situation where, actually, you know what? This is missing a line. This is not good. Let me just throw this away and draw it myself. So if you are really looking at a continuous voltage, and I'm just going to do 4 volts. So you go 4, 3, 2, 1, 0. And then you could represent that with the value of 0, 0, 0, 1, 1, 0, and 1, 1. And so you get to represent all of these and notice it's not exact, right? Because there's how many points here?
5.
5 points. And there's how many over here?
4.
Only 4. Well, we can get even more extravagant. Actually, I've got a nice picture in here. I should just pull this out. Where you can actually have it a little bit more wide open. So we have it between negative 10 and 10 volts. So it is possible for you to even have that much space. That's a 20 volt range that you only have 4 bits to represent. And so the resolution is not going to be as good. By the way, there are situations where, depending on your A to D converter in your device, you may actually miss one of those. And keep in mind that if we say that the digital representation is, in this case, 0101, it actually is the true voltage range right here. And I'm going to go into this in a lot more detail, but I just want you to understand the general concept that when you're doing A to D conversion, analog to digital conversion, you're not going to be precise. Only very, very rarely will you be exactly precise. It's kind of like, how precise is a clock that doesn't work anymore?
Twice a day.
Twice a day, right? Think about that. So, here's the main formulas that I bet you all want to find out about so that you can do the homework assignment, right? So I think I'm going to answer your question, Jeffrey, when we finish this.
Okay.
Oh, good. And that is our resolution of each bit is going to be whatever the V reference positive minus the V reference negative divided by 2 to the n bits, where n is defined as however many bits that you have. So Vref, the plus side of your A to D conversion, Vref minus equals the minus side of your conversion.
In the homework, you haven't given any values for Vref negative. Should we assume
Hold
that's
on. Usually, Vref minus is equal to 0 volts. And when nobody tells you what it is, assume it's 0. Because all chips work from 0 to VCC. And where you are not told usually VREF positive is equal to VCC. In other words, the voltage that the entire board is working on, or I should say the chip is working on. And then N bits, of course, what you store. So, for example, for the Renesas boards, you could have 8 bits, you could have 10 bits. I think this allows 12 bits, but I need to check that. And with more bits comes, what do you think? Worse or better resolution? Better, because you're actually splitting up the entire range into smaller and smaller pieces. So let's say I have my Renesas board, which is running at 3.3 volts, and I have 8 bits of resolution. The resolution of each bit is going to be equal to 3.3 volts over 256, because it's 2 to the n bits, which is equal to, where's my good mathematicians in here? Somebody with a calculator on their iPhone.
0.012.
0.01289.
89.
I'm going to stop there. Volts, right?
Resolution.
Pardon me?
Resolution.
Or 12.9 millivolts, right? So, as another exercise, board is equal to 3.3 volts, and I have 12 bits of resolution. The resolution of each bit is, figure it out with you and your next door neighbor.
Zero.
It doesn't go to the.
Good.
It's like 2. No,
Oh, I had. This was one of the prizes from the prize closet, and they were going to try and you did it too far, man. You're supposed to do it, like you do in concerts and stuff like that.
It's supposed to go up. And
Or graduation, so here you go. There you go. Oh, well, it's back there. All right. So I can imagine what the people in the video are going to look or think when they see that, right? At least I'm not throwing erasers at people. The answer of this is? All right, 0. 0. How many volts? 0.008.
0566.
Nothing like being precise, huh? All right, everybody get that concept, right? So now you know how every step is. Now let's say we have a certain voltage. So our certain voltage by the way, how many of you have had this already that I'm going through right now? Raise your hand now. You got to find out how many. Well, not that many, so it's new to, I know you. It's new to almost everybody, right? All right, because my fear is that somebody's already covered this in some previous class and, you know, you're sitting here bored. Which remember, you're supposed to tell me if you're bored, right? Thank you for bringing that up because things were getting boring. All right, let's say that your positive reference is going to be, I'll mix it up a bit, 5.0 volts.
Scroll down.
Pull it down a bit.
Which you're supposed to be able to figure out on your own because now let's say my V in is equal to 2.2 volts.
Does that mean VREF?
Pardon me?
Is that V reference minus or
No,
no?
that's not V reference minus. So I didn't tell you what V reference minus is. So what does that mean you assume? All right. And let's say I'm going to do a 10-bit ADC.
450.
Hold on. I haven't even got to the formula yet. So what you need to identify is that the digital representation, in other words, the N is equal to the digital code that represents 2.2 volts is going to be the following formula. It is going to be 2 n bits minus 1 times V in all over V ref plus. And you take this, oh shoot, did I do that right? You round it up. You take the ceiling or you take the floor plus 5. So in other words, you round it.
Always round up.
Always round it.
You add 0.5 and you round up. Or
Well, you take 0.5 and you take the floor. So I'm going to just say round up. So if we look at our formula here, so it's 2 to the 10 minus 1 times V in, which is 2.2 volts, and we're taking it over 5.0 volts. So that is equal to 1023, because that's 2 to the 10th, right? Times 2.2 divided by 5.0, and that is equal to what number?
450.412.
450. 450. Is it exactly 450?
0.12.
0.1?
2.2.
0.2.
1.12.
that's the decimal representation of the bits.
I'm going to do that, make it easy. So you add 0.5, and then you take the floor. Oops, it's not volts. Because volts divided by volts. So it'll be 450.
And that's equivalent to just regular rounding, right?
That's equivalent to regular rounding. And oh, by the way, it's not a voltage, right? It's a representation.
So
So inside the computer, what's the representation? Binary. So what's the conversion of this into binary? Well, let's take this. Half of 1024 is 512, and it's not that. So that's 256, right? Minus 128. Catch me if I do my math wrong. You're just looking to see if I screw up, I know. 6 minus 64. So, not 32, not 16, not 8, not 4, 2, 0. Did I get the right number of bits? Yep. Yay, I got it. All right. So that would be the representation in there, which, by the way, would be, oops, it's not 0x. It's binary, which is going to be 0 hex, 1, C, 2. You think you can do all that? Good. You're going to do one now. You know what? It's almost time to call it a day. Have I got everything done? I'm just going to say, I've done that. You can do your own on your own. You can do additional ones on your own. All right. I got 2 minutes. Even though you're packing up, I'm going to keep going. Four already? I'm on 5 already. We'll figure all this out. All right, so the last thing I wanted to cover is if you look in the discussion of power and ground and stuff like that, I just wanted to point out some things. You have battery life is going to be equal to the capacity minus the current. So if you have something that is, for example, 200 milliamp hours, that's like a small AA battery. And you have a device that's going to draw 10 milliamps at any one time. How long will it last?
20 hours.
20 hours. Now you have to keep in mind that if you have 2 batteries, and each of these are 1.5 volts, and you put them together like this, what is your output, or what is your voltage between these 2 points? It's either 3 volts or it's 1.5. Which is it?
1.5.
So it is 1.5 volts. All right? Assuming that this is plus and minus, right? However, if you take it like this,
Can you pull the screen up? 3.
your voltage is 3 volts. So if this battery stores 200 milliamp hours, and they're all 200 milliamp hours, what's the storage of this battery?
40 hours.
The storage capacity of this is going to be 400 milliamp hours. What's the storage capacity of this?
200.
It's 200 milliamp hours. Because you're either combining the voltage, if it's in series, or you're combining the capacity if it's in parallel. Make sure you understand that.
Yeah.
I almost guarantee you that's going to show up in a future homework assignment. And you can read about clocks separately. I believe that's all for today. Thank you very much.